Yeah. Okay, there we go. Thanks. Okay, so somebody, what's the value here? Okay, so sorry. Okay, so this tells us that if U.S. and China had exactly the same technology, you can account for the higher level of Chinese production if labor's share in both countries is close to 0.7 instead of 0.6. Yeah. I'm not going to crawl very far out on a limb to defend that assumption. What I'd like, what you should do is check it. I mean, especially for a back of the envelope thing like this, that I'm going to start with the simplest set of assumptions I can. If you think that's a suspicious assumption, that's not likely to hold, then the way to check it would be to do what I said before, which is to go get some more micro level data on labor costs for both Chinese firms and U.S. firms. And I frankly have no idea if they're similar or different. I really don't know. I do know that other studies estimating functions of Cobb-Douglas production tend to yield estimates of labor share that don't differ that dramatically across countries, even when there's big differences in wage bills. So this is a guess that's informed by other studies, but I don't know what the share should look like for PV manufacturers in particular. So, is there another question? Same. Okay. Yeah. Yeah, these are all. So there's some other details that could be important. So these manufacturing wages are computed using a PPP adjustment. If you use an exchange rate instead, you get something slightly different. I'm not sure if it will be larger or smaller. I think that's going to be a small change. I mean, I think you might get a number which is 10% different for that ratio or something. If you'd like to do this, I mean, really, this is looking at the numbers to do this kind of exercise is something you can do in 15 minutes. So feel free to improve upon my little back of the envelope exercise too. Well, it really is a technological. I mean, it's a technological parameter in this production function. So it says something kind of structural about the relationship between labor and capital, like for manufacturing, between labor and machines, or the production sort of technology. It's sort of interesting that in the U.S. at least, where most of these studies are done, we don't actually see huge differences across different manufacturing firms in labor share. And I said that the mean for the U.S. is around 0.6. Standard deviation isn't that huge. There's a puzzle related to the Cobb-Douglas production function. After you account for differences in what can change with these W's. So when we see variation in W, we see changes in costs that correspond to that. And it should be the case that the alphas, the alpha is also supposed to be constant. So if the alpha is constant at a point in time, and the alphas are both constant, but prices change, then over the course of business cycles, for example, we shouldn't see changes in our estimates of the alphas and the A's. In fact, we do see. So if you look at business cycle, if you look at the behavior of estimates of these things over the business cycle in the U.S., then the alphas don't change very much what the A does, for example, in a way that theory suggests it shouldn't. But on the other hand, the changes aren't huge, so it seems like a reasonable approximation to the data for a lot of industries at least. Yes.
Do you take into account salaries for executives or anything like that?
Yeah, that's a good question. So the U.S. data include that's for the entire manufacturing industry. So that's the wages of executives are included in there. For China, the data is you should be much less confident in the Chinese data than you are the U.S. The BLS, Bureau of Labor Statistics, does careful surveys of the labor force all the time and has really good data on this. There's no systematic survey of the labor force in China, and so the estimates of those wages are considerably less reliable. They're based on numbers from household surveys mainly. And I frankly don't know whether they include the full range of wages or not. Now that said, most manufacturing industries may have a CEO who earns considerably more than the workers. But there's only one CEO and there's a lot of workers, so the average isn't that affected. And also, the median wages for CEOs of manufacturing firms aren't as large as you think. They're on the order of $118,000 a year. I think it's the median. Okay. All right. Okay. Other questions? Yes.
So back to the demand part of things.
Mm-hmm.
So utility functions, so in our utility functions, the alphas represented with the consumer first, so that's just the behavior of the consumers. So in this case, the consumer side, the actual alpha quantity is selected based on their business curves and their budget. But in this case, are the alphas just inherently just the characteristic of the...
Yeah, they're a characteristic of the production function, exactly. Go ahead. That's correct. So that it's what we worked through last time was that the firm takes the production function is given, and they choose what level of inputs to choose given the technology. Now there's a possibility, and we might return to this later. If there are two different production functions available to it, or maybe there are two different manufacturing processes, and so those might feature, maybe they both Cobb-Douglas but feature slightly different alphas, then the firm can make a choice between those two. For example, yeah. So again, I'm not going to go very far out on a limb to defend this estimate in particular. It wouldn't be hard to estimate though. You could use the expressions we had for input demand we talked about last time, get firm level or even industry level data on this stuff, take logarithms of the input demand function and estimate those things. And that's a regression that anyone who's taken 118 would be capable of estimating. All right. Okay, so here's an example of how to use a cost function. The punchline is that there's not evidence here that the U.S. has a large technological advantage over China, rather the opposite, if anything. But the big differences in output are mainly accounted for by differences in manufacturing wages. There may be some scope for subsidies to skew things, but it's probably not very large because again, this difference is driving most of the differences in output across the two countries. Okay, let's keep going. So I'm going to keep going with the same sort of examples. We've talked about firm cost functions, and we've just worked with an example of one here. We talked last time about thinking about the firm's problem in sort of two stages. The first stage was to choose a level of output, or to think of a level of output y, and for any such y, to figure out a way to minimize costs. Having done that, once you get a cost function, the firm can solve the problem of trying to determine what scale to operate at. So I'm going to think about that second stage problem now. And the way to solve that problem is going to be to think about the firm maximizing profits. So again, we're going to assume here that firms are price takers. So here's the firm's problem here is to try to choose a level of output y. So y is in units of things like photovoltaic cells or something like that. the firm's going to face a price for its output of P, and it can't choose that price. That's what I mean by being a price taker. And then, so that's P times Y, or just the revenues for the firm. Price, the amount of stuff it produces Y times the price it can sell it at. So that's revenues. Its profits, of course, are just revenues minus costs. And we already figured out what the cost function is. So given a level of output Y and input costs W, its costs are just this cost function C of YW that we've been working with. Okay, so that's the firm. That's an expression for the firm's profits. It's traditional to use the Greek letter pi to do the profits. So we're going to get a profit function in a bit, and we'll see that those profits are going to be a function just of P and W. Now, why is it not also going to be a function of output Y? Well, defining profits here, the firm's going to choose Y optimally, given the prices PW it faces. And so it's going to have a unique choice for Y in what we talk about today. It's going to depend only on P and W. So that means we'll get a firm supplies. What we'll do next, in fact, is to get output as a function of prices. Once we've got that output, we can plug it back in, and we'll see the firm profits only depend on the prices it faces, and of course the technology it's operating. Okay, so this is a really simple problem to solve. We've sort of in principle at least, we've got a profit maximization problem. We've got a single variable to choose now, which is the level of output for the firm. So we've got this thing, this choice variable Y, and the first order conditions at this level of abstraction are really simple. What we have is just imagine taking the derivative of this thing with respect to Y. We just get P. This is the marginal revenue. This is the derivative of the revenue with respect to output. P is going to be equal to the marginal cost, or the partial derivative of the cost function with respect to output. Okay, so price is equal to marginal cost for a price taking firm of this sort. Okay, is that clear? Yes, sure.
So we're trying to maximize the total profit, right? So
Yes.
we want to maximize P Y minus the cost.
That is what we're doing. So C of YW, or the total cost of producing Y. Yeah. So it's the thing on the left hand side of the minus sign is revenues, total revenues, and the thing on the right hand side is total costs. Okay. Maybe I should draw you this picture. I don't have it on the slide. I'm almost sure you would have seen it in an intro course like EVE 1, but it might be worth reminding you. So here's output, and I'm going to have three different things on this axis. One of those things will be profits, another thing will be revenues, and the third thing will be costs. So here's Y. So revenues are just going to be a linear function of output. So this is the function Py, that's equal to revenues. What's the slope of this thing? Just to make sure you're awake. Oh, hold on, is it 1 or is it? So Y is here on the horizontal axis. P, yes, the slope of this thing is P. Okay, there's going to be a cost function as well. So maybe the cost function does something like this. Okay, so this would be or sorry, I'm sorry, wrong way. I want the cost function to look like this. Okay, so this is C of YW. Okay, now how do I know where profits are? Where does the firm maximize profits? I mean, well, so the profits, of course, are just equal to Py minus costs. So if I were to pick a point, along here, profits are equal to the vertical distance between these things. Where's the distance maximized? At the intersection? Did I get the intersection? Okay. Okay, so in particular, it's maximized where the slope of this line is equal to the slope of this line. That's going to be a point like this. Okay, so that's the modulo my graphing skills here. This is going to be the point that maximizes profit. Okay. So this is the point where marginal cost is equal to the price. This is the first order condition. I mean, the original. Look up here. The original first order condition is P minus DC is equal to 0. And if we look at the entire, if we look at, I'm sorry, I actually don't have profits here. If we look at profits, I think this is going to answer your question, Chris. As a function of Y here, you can see they start off at 0 at this point. They're 0 again here, and they reach some maximum. Let's see, at Y star. So I don't know, maybe something like that, I guess. That's what I did. This area here is this, right? Or minus here. And so yeah, this is the point where marginal. This is the same point Y star where marginal price. I'm sorry, price is equal to marginal cost. Yes. Yeah. Yeah. So let me come back to that later. But you saw I did it one way and then said no, do it this way instead. The reason is because suppose I had my original way, so something like that. Where are profits maximized for that function? Yeah. Well, so if you find the spot where the slopes are equal, which would be maybe here. What are we maximizing? We're maximizing our losses. Yeah. And so this function implies increase in terms of scale. We actually maximize profits by producing an infinite amount. So don't do that. We want to avoid that. Okay. All right. So what I want to do next is this graph clear? This is the first problem. I want to go ahead and do the example for our Cobb-Douglas case, and we'll work out the next thing. Oops. I wanted to see here. I want to work out the next an expression for the firm supply function. Okay, so we're going to be assuming the same Cobb-Douglas production function we've been working with for a while, and I want to just get this expression. This one's really easy. So we have, I can reuse it. We have this production function, this cost function. Now, what I want to do is just sort of plug in for this expression, P equal marginal cost. So to do that, all I need to do is find the derivative of this with respect to Y. So the partial derivative of this with respect to Y is itself a pretty simple object. So dC dy of YW is equal to what? What do we get there? Yeah, something here. What else? All this stuff is the same, so there'll be an expression W1 to the alpha, W2 to the alpha 2. That'll all still be here. I'll put it out, I guess. Okay, now what about the, and this is also to this power. I'll do that too. Okay, good. And then also the h to the alpha already. But now, so we've been putting out the inevitable here. Oh, there's also an a in here. Okay. So now we've got this piece. What's it? What value we get for that? Yeah, so it's y to the, I'm going to observe something, which is y to the 1 over alpha 1 plus alpha 2 minus 1 happens to be equal to y raised to the 1 minus alpha 1 minus alpha 2 all over alpha 1 plus alpha 2. Yeah. So this is the piece I need. All right, so this is an expression for the marginal cost. There's another. Yeah. Do you have a? Yeah, I split it up. I pulled the y out and raised it to the 1 over alpha 1 plus alpha 2, which I can do because multiplication is associative. And so all this stuff is what, as it was before. It's just a constant when we take the partial derivative. Yeah, I think I'm okay here. Now, so that's kind of that's not too horribly ugly. I'm going to notice something else about this though, which is that another way to do this would be to say that this is just equal to 1 over alpha 1 plus alpha 2 times the cost function cyw. So this whole thing. All I want to do to take the derivative here is get this exponent out front and have a y raised to the minus 1. So what I do is do this. That's also the marginal cost function. But for this case. Okay. Now I want to come back to this question about the marginal cost function. So how does this thing behave? Let's think about graphing this marginal cost function. So we've got y here. What does dc dy look like? Probably easiest to see this here. Well, there's one really simple case we can consider first of all. What if we have constant returns to scale? What happens then? So if we have constant returns to scale, what does that imply about the alphas? They're equal to 1. And if they're equal to 1, this numerator is 0. So the y to the 0 is 1. So marginal costs don't depend on output at all. Okay, well, that's what we mean by constant returns to scale. In fact, the costs don't depend on just the linear way of the scale you've got. So if alpha 1 is equal to alpha 2, then dc dy might look like this. Okay, was there a question back there? Scott? Okay, yeah. Okay, so this is the case where alpha 1 is alpha 1 plus alpha 2 is equal to 1. Okay, what if alpha 1 plus alpha 2 are greater than 1? Well, if they're greater than 1, then this is a negative number, right? So y will be in the denominator. So we have, if we make y really small, we might get something like this. Greater than 1. So the more you produce, the lower the marginal cost. And then finally, the case that is going to concern us here, because it's sort of the, we don't see that many firms producing infinite amounts of stuff. So the case that's going to interest us here, in this case it's interesting too, but here we're going to care most about the case where alpha 1 plus alpha 2 is less than 1. And so what's that going to look like? So if alpha 1 and alpha 2 are less than 1, this exponent is positive. Yeah, is it? You're pointing with the... Okay, so we just need the, well, let's take an example. Let's say that alpha 1 plus alpha 2 are equal to 1/2. Then what do we get here? Then we get 1 minus 1/2 is 1/2 divided by 1/2. So that's a case where if y is equal to 0, marginal costs are 0. But otherwise, this thing will be increasing at a linear rate. So this is the case where alpha 1 plus alpha 2 are equal to 1/2. Okay, so that tells us two more cases that might be interesting. One is the case where alpha 1 plus alpha 2 is less than 1/2. What happens then? Then we've got a number. So less than 1/2 means the numerator is more than 1/2. It's less than 1/2. So it's a number greater than 1. So we get something like this. Okay, yeah. And then finally, if alpha 1 and alpha 2 are between 1/2 and 1, we'll get something that might look like this. So increasing marginal costs for all three of these cases, but at different rates. Oh, is that sort of clear? All right. All right. So that's marginal. That's a characterization of the marginal cost function. Now, why should we care about the marginal cost function? Well, here's a reason. Let's think about